Good morning. My name is Kaushik, and today my topic in big data and business analytics tech talk is about our dynamic future. So, coming to the introduction, last month as I tossed my bags in a rental car at the airport, I noticed that the car was particularly new. I was quite surprised, however, when I drove up to the first stop sign and the car suddenly died. So, this is a story which follows about our dynamic future. It was as if I had run out of gas or turned off the ignition. However, as soon as I took my foot out of the brake pedal, the engine started itself back up. I pushed on the accelerator and the car jumped forward. Over the next couple of days, I explored this advanced fuel saving feature that trying to understand under what circumstances the car algorithms would decide it could save gas by temporarily shutting off and how quickly I could jump forward after moving my foot from brake to accelerator as the car automatically started itself and slowly adjusted the throttle. Dynamic power management is everywhere, from cars to mobile phones to home heating and cooling. One of the key technology changes making advanced power management possible for your automobile is the shift to fly-by-wire controls. The driver only indicates intent. An internal control system then selects the optimal throttle setting or brake pressure, all in an effort to improve efficiency. Modern high-end CPUs follow this pattern, and this new reality will fundamentally change how we write extreme scale applications. For years, CPU optimized for the mobile market has been designed to automatically reduce power by lowering chip voltage and clock frequency as computational demand decreased. The reduction in power could extend battery life in the high performance computing domain. This feature was frequently disabled so the CPU could run at full clock speed without slowing down to save fuel when the program drove up to a stop sign. In 2012, Barry Rountree and his colleagues at Lawrence Livermore National Laboratories reported that, to their knowledge, none of the systems in the top 500 use DVFS to save power or energy. Data reuse can improve cache performance to decades for decades. An assumption reflected in our abstract machine is that equal work executes in equal time. Programmers understand that if equal sized chunks of work are distributed across an extreme scale platform, the CPUs will execute the work in equal time unless there is a significant anomaly. Algorithms are designed to work efficiently so long as the model remains correct. Equal work executes in equal time. However, if one CPU is slow for some reason, the entire computation often becomes slow as the slowest CPU. The fastest CPUs arrive at a barrier or time step early and then spin wait until the last CPU completes its work. Experiments have shown many reasons for why a CPU might be slower. It could have faulty RAM and be forced to do error correction periodically. Maybe a misconfigured system script is running in the background, or maybe the node is at disadvantaged in the interconnect topology, sharing switches with other jobs. Whatever the reason, when equal work doesn't execute in equal time, the abstract machine model fails, and many HPC algorithms perform poorly. Therefore, DVFS has largely been undesirable in HPC. Allowing even one CPU to slow down to save power could impact thousands of other CPUs waiting for the chunk of work to complete. Boosting more power. Although DVFS was largely a technology to save power and could be disabled, today's high-end CPUs can only burst up to maximum performance for short periods of time before automatically slowing down. They simply can't run at maximum clock speed for an entire HPC job. Their highest performance can be sustained for long periods. On Intel CPUs, this feature is called Turbo Boost, but all CPU vendors have a similar feature. For example, on an Intel Haswell CPU, the base CPU clock speed is respectable 2.3 gigahertz, but for short periods, one or more of the cores can burst up to 3.6 gigahertz before the internal temperature forces the core back down to a more modest clock rate. Essentially, the clock speed can be boosted by more than 50% for very short periods. Even more remarkable is the Intel Core M CPU designed for the mobile market. The baseline clock rate can be boosted 140% for shorter bursts. Largely, HPC centers facing an interesting set of choices. Turbo boost can be disabled and chips prevented from ramping up to their highest levels of performance for short periods of time, thereby eliminating a source of variability in system performance. Or turbo boost can be enabled, allowing CPU to periodically achieve higher performance, which increases the variability within the system and breaks the equal work executes in equal time model that so many algorithms expect for good performance. Many HPC centers have decided to enable turbo boost, and yes, the individual performance of each node is now more variable. More importantly, our future is now a little clearer. For example, the challenges of power and resilience have been heralded as game changers for exascale. But how do those challenges translate to the impact on computational scientists writing a large-scale applications? Power and heat are precious resources. As we push toward more powerful CPUs, heat and power management will continue to be handed over to complex internal CPU control systems. While the certainty, much room, and need for research into how software controls could link with compilers to predict where and for how long to temporarily use turbo boost modes. At this moment, the CPU's internal control system runs the show. Go over the speed limit for too long, and no matter how hard you stomp on the accelerator, the CPU will begin to slow down until the engine can cool off. Computational scientists should expect more performance variability in CPUs. The abstract machine model that assumes equal work executes in equal time must be replaced with a model that assumes execution times with significant variability that could average out over longer frames of reference. From a programming perspective, overlapping computation and communication is good, but not sufficient to address this new need. The programmer must also work with advanced runtime layers to absorb short-lived slowdowns on some nodes or possibly manage dynamic workload balancing. Of leadership, computing, November or December 2015 course. Some computer science researchers have already treaded this path. More dynamic programming frameworks such as Charm++, Silk, Argobots, and Parsec are available, and scientists have been exploring this space. The question that remains unanswered is how dynamic our programs will need to be. At this point, we know the trend, we know the performance impact for some classes of problems, and we know the trend will continue. However, we don't yet have a good understanding of how much dynamism must be available in the runtime system in 8 years. We can safely recommend that users begin exploring whether algorithms assume equal work executes in equal time, and how algorithms could be refashioned and runtime systems used to efficiently execute code on tomorrow's leadership platforms. Thank you.